All right, welcome everyone. I'm gonna wait just a few seconds to allow people to trickle in. All right, we'll go ahead and get started. Welcome to our third session in the embodied carbon track. If you're joining us from the last session, you just heard about sustainable mass timber forest product procurement and bamboo procurement. We're here to now take that to the next step and talk about how do we actually design with mass timber, what are the construction considerations, and what are innovations in this field that we can anticipate. So the learning objectives for the session are shown here, and as for all sessions, we'll be following up with a survey to get AIE membership numbers, so stay tuned for that. We'll also collect all the questions submitted because we likely won't have time to get to all of them, and we'll ask our panelists to respond to those and we can post it on the CarbonPositive website later. All right, and with that, another reminder that all sessions have live simultaneous Spanish translation, which you can access via the globe icon if that is of interest. And with that, I will introduce the speakers in the session, and I'll keep their intros brief, but their full bios are on the CarbonPositive website. So our first speaker will be Michael Green, who really needs no introduction in this realm. But in case you're not familiar, Michael Green is an award-winning architect known globally for his research, leadership, and advocacy in promoting innovation in the built environment, and wrote the book on innovative modern timber construction, The Case for Tallwood Buildings, in 2012. Our second speaker will be Kristina Miele, a senior engineer at Bastinet's New York office. Christina has worked on a variety of mass timber projects, most recently one of the first buildings to adapt to the 2021 Tallwood building provisions in IBC. Christina also has a strong background in embodied carbon. She founded New York's chapter of the Embodied Carbon Network and leads the Embodied Carbon Subcommittee for AIA New York's Committee on the Environment. And our last speaker will be Don Davies, president of MKA, a 200+ person international award-winning structural and civil engineering firm headquartered in Seattle. Also a leader in embodied carbon lifecycle analyses, Don is a founding member of the Carbon Leadership Forum. All right, with that, I will pass it to Michael.
Great, thank you. Hi, everyone. Oops, there we go. And I'll just grab this. Wonderful. So, hi, I'm going to speak for about 10 minutes, and I'm going to just do an orientation on mass timber to kind of kick things off. So my firm's up in British Columbia, and we are a 100% wood firm. So we're committed to the idea that for now, wood and structure in particular is the best way for us to go to create carbon sensitive, carbon neutral buildings. Our work is super diverse, and I'm just going to show you really quickly a couple of images of ongoing projects, ranging from work we're doing with First Nations communities to a building here, an office building we've just completed actually in Washington State that's net zero energy, net zero carbon. Buildings in Paris, France, made entirely of mass timber and residential. So this one's just coming through the tail end of design in Paris. And then buildings that are super tall buildings that we're working with companies like Google and Sidewalk Labs, really to see, what the future of big buildings, big urban scale buildings might be. And so this was in Toronto with Sidewalk Labs, a 35-story tall building we were looking at. So for orientation, that's the kind of thing we were up to. And, of course, the question is why? And of course, the answer is what you all are participating in the conference about. And that's that big footprint number of CO2 emissions that buildings have, and that 39% that we talk about globally. And of course, repeating what you all know, I'm sure, is this target that we've had of 1.5 degrees centigrade rise over the next, to the end of the century, which would mean that we would all have to be at peak carbon today, this year, down 45% by 2030 and net zero by 2040. So all of us in the building industry obviously know we have to make a dramatic change as quickly as possible in all kinds of ways. And we have to do that because roughly 2.5 trillion square feet of buildings have to be built between now and 2060. So if we use the technology of our day, obviously we are in desperate trouble from a climate point of view. We have to build effectively one New York City every month for the next 40 years. That quantity of building requires a systemic change in the way we think about how we build, or else we're in a lot of trouble. The breakdown, as again, many of you will know, is that 39% the building industry relates to is roughly 11% embodied and 28% operational. So embodied being what the materials of the building themselves are. And so CO2 is obviously emitted in the manufacturing of the building materials is fundamentally the issue. And when we start to consider that operating, heating and cooling a building versus what the materials of the building are, that operating is almost twice as much as what the materials are, 3 times as much as the materials, you might ask yourself, well, why not focus more on heating and cooling? And of course we should. But the time value concept is really important to consider for all of us as builders and designers. And the time value concept basically simply says, and this comes from Architecture 2030 site, that over time, every year we're increasing the operating carbon of a building. So each year, eventually, we're going to rise the carbon footprint from heating and cooling to a very large number. But the first day we build the building, roughly 25% of that building's carbon emissions has been made. So the intersection point is the important thing, where the heating and cooling intersects with the footprint of the embodied carbon, the materials in the building, happens today on average here in North America, 15 years out. But as we reduce our heating and cooling impact, as we move to renewables, that sloping line from operational carbon will be reduced, and that intersection point will extend further and further out in time, meaning what we build buildings out of, that structural material in particular, the volume of material, makes an even bigger difference. And so roughly between now and 2050, almost half of the carbon story of buildings, depending on lots of variables here, is the material you build the building out of itself. So the 2 things we do fundamentally to impact our global carbon emissions is to reduce our carbon and to capture carbon. And what's important for wood and forestry, and why this talk is happening, is that it's really about the fact that the forest gives us this natural carbon sink, and that when we harvest wood, and if we do it from sensitive forestry practices, it means we effectively, on average, store about 1 ton of carbon dioxide in every cubic meter of wood, as long as we source from appropriate certified forestry practices. What that starts to look like then is when you are choosing a structural system for a building, this sort of general trend is what the carbon footprint looks like. And you can see on the right, the least impactful would be wood buildings ultimately in almost every single environment we look at. So as we move in general from this idea of a very linear economy to a very circular economy, we believe that wood, and the reason, again, my firm has decided to be 100% timber company, is that ultimately it's the only pathway to a truly circular economy. So we've decided more wood, more urban wood, being where most buildings are built, and more tall wood, which really comes to the idea that we have to change the scale of the way we think of wood products in buildings. And that change is what mass timber is all about. So on the left, you have a cross-laminated timber panel. On the right, you have a piece of dimensional lumber, a 2x4, as we'd say in North America. And these are 2 very different things. They're 2 different things structurally. They're 2 different things from a fire point of view. And they are 2 different things from the point of view of scale, how big a building we can make. So what we know is there's a family of products now that are available. And these have been evolving over the last really more than 25, in some cases 75 years with Glulam. These products have existed, but we're now starting to see them used in whole new ways. And so this is a family of products that we call mass timber. Up in the top left, cross-laminated timber is kind of the product that probably sees the most attention, but really laminated veneer lumber in the bottom left, dowel laminated lumber, laminated strand lumber. There's a whole bunch of different ways of thinking about mass timber, each having a sort of appropriate use, each having a slightly different carbon impact and regional impact when you choose them. So just really quickly with my time, I just wanted to highlight a kind of quick case study that we did. So this is the Wood Innovation Design Center located in British Columbia, and it was our first tall wood building as a firm, and really it was the second tall wood building in the world and first in North America. And it is 100% wood building. So the elevator core, the stair core, everything is wood after we left the ground. The foundation's concrete. After that, even the curtain wall system was wood. But what we wanted to show is, although it's not super tall because the building didn't need to be, how could we do this using a mixture of glulam, post and beam, and cross-laminated timbers? And so we don't have time today to go through in the detail of how these buildings work, but they're quite sophisticated buildings requiring a really integrated way of thinking. So we worked very close with mechanical, electrical, and structural from the very earliest concepts, because of course these kinds of buildings are new. And integrating services into the structural design was something that we felt was really important. So the idea of shifting to mass timber starts to open a whole bunch of big questions, technical questions, fire resistance and resiliency questions, acoustic questions, and erection questions, and of course structural questions as well. And I'll leave those questions for Dawn to dive into, I think, next. But when we did this, this building, we also did a full building life cycle assessment. Actually, 2 different organizations helped us with this. And what we found is that one building effectively was an 88% CO2 reduction when compared to a concrete building. And when people often ask me, well, do we have enough wood to make buildings like this? The interesting calculation that we used using the calculator from the carbon wood calculator is that every 4 minutes, the North American forest grows enough wood to build that building. So the forest is constantly growing. Of course, we don't harvest from the full North American forest, but the point, of course, is this is a renewable material, giving us a chance when we do mature our forestry systems to make sure we're harvesting forest responsibly. It gives us a chance to grow our buildings and meet the demand for buildings of this kind of scale. So that as a case study sort of highlights the last few points I want to make, and that's the story of, again, of why. So there's the environmental story. There's also a full cost story. I won't go into the details right now, but I welcome questions about these things. Saving time, and ultimately health and jobs. And that's the other big story with mass timber. It's not just about using a renewable material grown by the power of the sun that sequesters carbon. It's also about the fact that we are increasingly learning the concept through the concept of biophilic design, that buildings where we surround ourselves with natural materials, increase our work productivity, increase social connection, decrease stress, ultimately help physical healing and learning and general emotional well-being. So the material choices we're making are dynamic, they're important. And this new way of building, we believe, will be incredibly important for the future of our cities. So the last thing I'll just mention is that these buildings can be very large, very tall. We're at the beginning of an evolutionary change, and we welcome architects from around the world to kind of join this revolution of the way we can build more carbon neutral buildings. So with that, I will say thank you and pass the torch.
Great, thanks, Michael. So I'm going to take over from here. My name is Kristina Miele, and I'm a structural engineer with Fastenap. I'll get this going. So Fastenap is a structural engineering firm. Our home office is in Vancouver, BC, and we also have offices in Calgary, Edmonton, as well as US offices in Seattle and New York. So I'm based out of the New York office. Over the past 20 years, we've started to press work in mass timber and have really kind of created a specialty in this realm. We have over 300 projects, mass timber projects, as well as over 10 million square feet of mass timber projects throughout North America. And I thought to kind of build on what Michael talked about in terms of the why is, once we dig into some projects and kind of what have we learned from those projects, so a little bit more into the how. So in the projects we've done, I think there are some key lessons that Michael even touched on in his talk, that grids, acoustic, MEP integration, fire, procurement, and cost kind of, for me, are the big ones that come up as questions over and over again. You want to look into designing a mass timber building. How do you start to think about these things? So I'm going to talk about it from the perspective of 3 case studies that are kind of had 3 different goals and 3 different clients and what those looked like. So I'm going to start with Brock Commons, the Tallwood House, which is a a dormitory at the University of British Columbia, 18 stories. It was at the time the tallest wood building in North America, which is going to be taken over very quickly. And the goal here in this project was for the university to kind of push research in this realm and say, how can we go tall quickly and kind of prove a successful demonstration of the economics of a tall wood building. So what you have here is a point supported system, which is a very tight column grid, which was a good choice for a university dormitory with small rooms, but may not be a great choice for other building types. But really here it worked well. It was able to eliminate all of the beams in the building and just have a flat slab building. So what this project successfully demonstrated was that it is possible to build tall with wood and make it, in a cost comparison, very comparable to a concrete building. So for the cost of construction, this building was $36 million, and that came into around $221 a square foot. This is in Canadian dollars at the time, which was very comparable to a concrete building at $220 a square foot. And it's really making its way to become even more effective over time. And one of the reasons for the cost savings is really the coordination and collaboration that allows the building to go up quickly. So here's kind of one of our favorite images of a very small construction crew. So basically on site, there's half the workers that you typically have on site, with buildings going up at 2 times the pace. So for this building, they were able to construct 2 floors per week. And as you can kind of see in some of the images here, everything is prefabricated, pre-coordinated, and pre-cut. So you can see the holes that are kind of accommodating some of the column connections, some taped up holes below the workers on site. And then 2 floors behind, there's a prefabricated facade system that was being installed. It took about 8 hours per floor to install all of the prefabricated facade system. So this project was really a great example of collaboration and kind of a success story in how, when the team works together and through a lot of research, could kind of pull all the pieces together that make a project like this make sense. And the facade being a really important part here to enclose the building very quickly as it was being built very quickly as well, and protect it from weathering. Another project which is currently in design is the Walmart home office. And this is for obviously a corporate client and a corporate scale, which we're seeing a lot of these days, but really an economy of scale. So not only thinking about how do you make these projects make sense when you go tall, but when you have a large campus with many buildings, how do you make it make sense for the economics, which is similar to the economics of Brock Commons, but kind of taking that area and spreading it across a large system. So here we have multiple buildings, most utilizing mass timber systems where it makes sense to do so. And really not at the exclusion of anything aesthetic or building performance wise, and kind of working with the client with what their requirements are for the feel of the building and the requirements, while not taking away anything aesthetically from the building. And then third, this is the Intro Cleveland building, which is just about to be under construction in Cleveland, Ohio. This was one of the first adapters of the 2021 building code, in that it was pushing the height limits that the current building code allows for tall wood buildings. And this was both a challenge, has been a challenge, and also really exciting to kind of work through some of the intricacies of the 2021 building code. Here we were in type 4B, which is a max of 12 stories, and it requires a partially enclosed building, which means that not all of the timber is exposed. Some percentage of the timber is required to be encapsulated or covered in drywall. So this was an interesting study in showing, working with a developer and understanding how is this new code going to apply outside the realm of Brock Commons, which is the tall wood in Canada, which was fully encapsulated, and start to expose more wood in the US under a different code. So within these 3 projects, I'm going to talk a little bit just to kind of go over what we've learned in a little more detail. But as a structural engineer, we're always thinking about how to kind of find the balance between reducing carbon emissions, which really comes down to what's the basis of engineers' work, is to simplify a design and think really closely about how the structural efficiency works without sacrificing aesthetics, project criteria, constructability, kind of always trying to strike the balance between these 2 points. So the lessons we've learned throughout these 3 projects and many others is the importance of grids and vibrations. So here is a quick 3D visualization, not a great one, but a study of what does it look like if you have a purlin system versus a not purlin system. And this is one of the ways where we see the balance of cost versus aesthetics, in that this one tends to be more cost effective because you have thinner panels, and this one is a little more pleasing aesthetically depending on the desire of the client. What we found in a lot of our projects is that you can look at so many different grids and combinations that it really becomes an overwhelming task when you're trying to find the perfect system. So what we did was we developed an internal tool where you can parametrically play with the dimensions and stories of a building, and as a client or early designer, get a sense of how much material volume you'll have at different scales. Other lessons we've learned is in MEP integration, how critically important this is, not only aesthetically, as you'll see in the left picture, but how important it is to get it designed and coordinated early on so that you can have these prefabricated holes arrive on site and really pull from all of what we're looking for when we're designing a mass timber building and having it all done in the shop. From a fire perspective, and this really is the question I'm asked most often and what we learned most about, especially in the intro Cleveland building, when you're designing a building, regardless of whether it's concrete, steel, or timber, you're designing to the required fire rating for the code. So what we had in the intro Cleveland building is a 2-hour fire rating on the timber. And what that means is that we're following very closely with the NDS how much wood needs to be left over in the fire case to prevent any catastrophic failure, which means all connections are protected from this char layer that you see develop on the outside of the timber, and everything has to be detailed to a very fine point to make sure we're accommodating wood that's exposed in a fire case. This is accomplished in concrete by covering the concrete, and in steel through intumescent paint. And wood is very much the same, requires the same time as other buildings, just that the mechanism for treating the wood is really built into itself. Procurement is another big one. We've learned a lot about different types of procurement and getting the fabricator involved early to really understand the constraints, what size panels they can deliver, how wide the panel is, what the connections might look like, when the panels are available, and kind of looking more into the fabrication of a building early on in the design, more so than you would for steel or concrete. And then thinking about cost, which Michael touched on a little bit, but how there's a savings in cost with schedule that was shown really in Brock Commons, but in a lot of buildings that are thought of this way. You're able to reduce foundations, less soil remediation, and smaller foundations for a lighter building, faster erection on the timber, earlier start on the envelope, and a lot of the MEP is coordinated ahead of time, assuming you have a well-coordinated design team, which really cuts down on schedule and is where a lot of the cost savings comes into play. And then kind of leading into what Donald will talk about a little bit more is, a lot of the buildings I was talking about are more post and beam systems, but as you start to develop this, how can you go taller with timber? Here's a study we did on a tall timber building in Seattle, but how can you kind of push the concepts of aesthetics, lateral, materiality to kind of do something more than your typical post and beam system? So just one more case study here is a project we're working on in Eastern Canada for James Brown College, which is a system that isn't quite your traditional post and beam, but relies on thinner panels spanning between thicker panels that kind of rest on these CLT wall systems. And it's a system that's composite with concrete, which really gives you this flat slab look that you had similar to the Brock Commons building, but allowing allowing us to do much further spans. So as we work through these designs, we're learning how to push the boundaries within the realm of CLT and mass timber, and into the realm of other materials as well, which puts me over to Donald.
Thanks, Christina.
Sure.
So let's go for share screen 2 for myself. There we go. Are we looking at, hopefully looking at the screen says MKA. So for my section here, I want to pivot and start talking a little bit more about the fiber level, what I call a bio-based design. You know, an interesting fact is when loading wood in the direction of the grain, flaw-free Douglas fir can have over 8,000 pounds PSI compressive strength. That's stronger than most of the concrete that's going to be under our feet in many of our buildings. But when you change that wood 90 degrees and you load that wood cross grain, the cells crush and it's less than 1/10 the strength. Now, my point with this is just simply that paying attention to the direction and the type of fibers used, it matters in this design. And challenging the architects in the room, it also opens up a world of creativity and innovation that, you know, I think our industry is just starting to explore. It's fun because nature has a thing to teach us on what we can do for the optimization if we're just paying attention to what we're doing with those natural fibers. So I want to go down this venture just a little bit more. And in particular, as a structural engineer, I'm always looking for the answers to problems and the optimal answers. And so I want to talk about nature's fastest growing fibers at the moment that we could use at a scale, which is going to be timber bamboo. Now, bamboo can grow in 4 to 7 years what it would take 30 to 60 years to do in timber. And that's really the carbon sequestration and value proposition here of just what this can do. The reason for this is fascinating. When I spent a lot of time looking at it though, it's really about the roots. In a tree, similar energy goes into growing above and below the ground what it takes to make that tree. But when the tree is harvested, everything that's below the ground dies and has to be recreated on every new tree. Bamboo, it comes from the grass family. And so what happens, when you cut a bamboo stalk, the root structure stays alive when it's cut. And so in fact, over time, it's one of the reasons it's so hard to kill bamboo for those of us that have planted it before is the root structure continues to mature and grow with time, and all the energy goes into the vertical growth of what happens above grade. So that's really why bamboo grows as fast as it does, is the plumbing below grade stays there. But bamboo also has about twice the strength and twice the stiffness of what timber or pine will have. And that really brings us to its value as a wonder fiber if we're gonna start looking at bio-based materials. Here's a couple of recent studies highlighting bamboo fibers growth difference and carbon sequestration with different species of wood and bamboo. And of course, the bamboo is the gold or yellow bars in the back, or some of the faster growing material. Now, the reality is bamboo doesn't grow everywhere in the world though. It has its sweet spot, and there's a lot of the country and the world where wood is going to grow. So I really don't think this should be an either or conversation. It's really about both. And frankly, if we are going to be moving into the, let's call it the bio-based world of construction that Michael was talking about earlier, we absolutely are going to need both at the speed of what we do, which is where I want to go when we talk about fiber, what I call fiber optimized design. Even today in the normal wood construction, we're paying attention to the fibers, and we take advantage of this to be most cost and materially effective. So like when we're doing a Glulam beam, the layups of the laminations in a Glulam beam use different species and grades of lumber on the exterior fibers versus the interior to improve the performance and capacity of that Glulam beam. Integrating bamboo into the extreme fibers of something like this, of a layup of a bamboo, to me is a natural progression of an optimization. And the right sweet spot isn't really an either or, it's figuring out how to use these fibers to their greatest advantage and mixing them together. So here's another example of bamboo and concrete being used together in a composite system, maybe a little bit like what Lindsay was showing there with Fast Enough with their CLT in concrete. If you can get the two to work together, use the materials at what they are best at, concrete and compression, using the wood or the bamboo as large surface area as the formwork, using it as the tensile component of that slab system, it can be extremely effective. This is a product by Resource Fiber where they're using kind of a nail laminated timber version of a bamboo plank with a composite concrete topping on the top of it. Blended wood and bamboo fiber optimization as a topic, it's just starting to grow. This company, Bamcor, is starting to bring products online with a plant that they are just opening up right now in Florida. And what's exciting here is I think bamboo is probably one of the first developments I'm seeing where it's taking bamboo fibers at scale and starting to come online with a plant that we can start using this at volumes that are more than just kind of one-off specialty applications. Now, the maze of approvals for bringing new materials online, bamboo or others, when it's a material that has life safety applications, it takes a lot. In fact, I'd argue that it's a very highly dysfunctional part of our building industry right now. So it takes years to bring these together. But if bio-based materials are going to be part of our future, leaving you with the point of fiber optimized design, be it wood or bamboo or other materials, is clearly in our future. And especially if we can start using these fibers in conjunction and together where they are most cost effective, bamboo offers incredible promise. So bamboo isn't there with the infrastructure to be there at scale yet, but with time, if we're serious about it, I gotta believe its prominence is only gonna continue to grow, pun intended. With that, Lindsay, I'm gonna turn this back over to you and we can talk about other systems or take some Q&A.
Wonderful, thank you. And with that, I'll invite Michael and Christina back as well. All right, so we've gotten a handful of questions related to fire in wood buildings. Can you touch on fire resistant of mass timber products and how you're addressing this within your design?
Sure, I'll take that one. Kind of as I touched on, there are two ways to achieve a fire rating for timber. One is through gypboard. So what the IBC says is that a 5/8 layer of gyp provides a 40-minute rating. So depending on the number of layers of gyp that you have some passive protection from gyp, and depending on how tall you are, you're actually required to have some passive protection. For exposed buildings, so in the range of like 6 to 8 stories where you're allowed to be fully exposed, the fire rating is all built into the char of the timber, which burns at a rate of about 1.5 inches per hour. So you'll find bulkier members as you go with higher char ratings, basically, but it's just different mechanisms of supporting providing fire protection than you'd have for other materials.
Great, any other comments on that?
Lindsay, I'll add something to it. The comment I'd like to make, fire is a good question to ask when we're talking about mass timber buildings. I would really venture people to look into performance-based fire engineering when you're really going to go down the space to find the best way to find the right application of materials, because the prescriptive codes aren't always going to be on target for where a lot of our mass timber solutions are. What I would also say, though, when we start talking about the taller buildings that we make them in wood, especially if we're using materials what they're most efficient at, fire is the bigger issue than structure to make these taller buildings stand up. How we manage the fire is a topic, how we manage the hazard, it really is the challenge, and to get the economics of it to work. And if we get the fire engineering right, absolutely we can be going much, much taller in wood structures.
Great, thank you for that. We have another question around embodied carbon and LCA. So can you address some of the criticism about the end-of-life carbon release of wood? Assuming worst case, it is incinerated, it is still better than steel and concrete. And how should we best dispose of it if we can't reuse it?
So I'll jump in on that. So you know, I in general, there are, as you've seen today, there are a bunch of different structural approaches to how we build these buildings. And like Christina, we've done some buildings where we do integrated concrete with the wood. But more and more we're leaning away from that. And the reason is we're trying to do what we call dry buildings for the most part, meaning there's no concrete, no wet products that bond to the wood products. And the reason is I tend to personally believe that the value of these buildings remains higher typically than another type of building. So it hopefully has a longer legacy, but that actually deconstructibility means that these panels have huge value. So much like I think of it as, you know, the way we're now taking down old barns and salvaging beautiful barn wood. I think these buildings, if constructed with disassembly in mind, actually give us an opportunity to recycle the materials in perpetuity very often, because with a well-maintained building envelope, these materials will last for, you know, many, many, many generations. So that's one way to think about it, is the structural choice actually does relate to that end of life story. And then, you know, the other opportunity then is that, and sometimes folks calculate into LCA is when that opportunity is to downcycle the material into a biofuel, which personally I don't feel as strongly about, because I'd rather, you know, create legacy product, but it is part of the story that some will use.
Great, Donna or Christina, anything additional to add there?
I'll add one thing. I think Michael brings up a really good point of the dry construction so that you can reuse the material. That's absolutely how you get to the reuse of the material. A topic I don't think any of our industry has solved enough is when we talk about resiliency and just how long we build these buildings for. And this isn't just a wood issue. When we talk about concrete construction or steel construction, when we make a steel beam composite with a concrete topping slab, I can guarantee you're not going to economically be able to save that steel beam, and you're going to tear it down and send it back to the mill and reuse it. But I can also tell you that composite beam uses about a third less steel than if we made them separate pieces and did just a steel beam and a separate concrete. So thinking about deconstruction really has to be tied into how long of a building are we going to last. I live in a 100-year-old wood house, and it's a stick-framed house, and it's doing just fine. But we need to be very thoughtful of when we go composite and when we don't. And it really has to be tied to the durability and resilience of what it is we are creating. The worst thing we can do is do composite construction that you have to throw it away and then tear the building down after 25 years because it's functionally obsolete and it's not going to last.
Excellent comment.
Yes, absolutely.
Yeah. I think I just want to add one last part, is that there is a time and a place for composite. I think that's quite correct, that we tend to avoid it, but there are places where it just makes sense because of vibration as a structural challenge very often in these wood buildings and certain types of uses, say a laboratory or space or something like that. We might end up doing composite again, I think, to Don's point, because it gives that building both its functional character, but also longevity. You know, you build a lab with too much vibration and it doesn't work for instrumentation, all of a sudden that building's obsolete. It makes no sense, right? So that's a well said point. Thanks, Don.
Great. I saw a question earlier regarding HVAC integration and mass timber systems. I know, Michael, you had a project that had a really innovative approach to incorporating MEP. Do you want to talk about that a bit?
Yeah, so I do think it's important as an architect to say that the process of how you design these buildings is, I think, quite different than the process of designing in steel and concrete. I think all too often in steel and concrete, the architect, you know, proposes a form, hands it to the structural engineer or the mechanical engineer and says, you know, fit all your systems and I'll drop a ceiling and it'll hide all those systems. In a wood building, that's just not the case. And so when we start a design process, we really have the mechanical, electrical, structural architects all in the same room together, sketching on the wall, working through the structural system, how sprinklers are going to work, how ducting is going to work, what is the appropriate mechanical system. From the very beginning of the process all the way through, it is a very integrated process, which I love. And truthfully, because we've been doing this so long, I didn't realize it was unusual. But, you know, and so people used to ask me about integrated design process like it was a new thing. And I didn't even know what they meant, because it's just the only way you can, I think, successfully build a wood building.
Absolutely. Christina, did you want to add something?
Yeah.
Go for it.
It's interesting because having started my career as a structural engineer, working mostly in concrete and steel, mechanical was kind of always an afterthought, or was fit through in places that I didn't have to think about. And now as we're reviewing CLT shop drawings and seeing the number of holes, it's really eye-opening to understand the mechanical systems in a deeper way, and also just thinking about the design as a whole. So whether it means having shallower systems in the hallways and really packing the mechanical into a certain area, but rather than getting the mechanical later on and trying to find places for it, it's really great to think about it as a team, and it makes it more of a puzzle early on to kind of fit all the pieces together.
So sometimes I think this is maybe one of the most fun parts of it, is just that, is that you can't ignore anything. It all matters. And so it is like a puzzle. I think that's a great way to describe it. And the opportunity to innovate, and the huge, you know, open, free opportunity to innovate in the future is around these issues of figuring out, you know, a better way to get mechanical into these buildings. Because the least expensive way is still all exposed mechanical. And that's not a great, you know, that's not as great, and certainly not as innovative as all of us would like to be in concealing systems, but still being able to expose the wood.
Absolutely. All right. Dawn, we have a couple questions on bamboo, and I think I can combine them. One is asking what you think about BAMCOR's SIP panel system and its applicability in buildings, and then any possibilities for bamboo trusses in the future.
Sure. The second one I'll answer first because it's easy. Absolutely. Bamboo trusses. It's all about using the fibers and creating materials out of them, and you could make those today. I don't even know that's it's just a future. The BAMCOR panels, BAMCOR created something that they call a prime wall, which they've built a couple of buildings with now as a really innovative system. It's basically a cavity wall condition off of some very robust plywood laminates that gives you an air cavity, so it has both acoustical and thermal insulation as an exterior wall panel. But what's also great about it is a really easy place to run all the MEP, or not MEP, but at least the electrical wiring if you're like doing a house inside that cavity, which is great. They're coming online with a next generation of that panel, which I think is even a better improvement, because the first one had a bamboo core with plywood on the outside, and now they're flipping it around to where they're putting the bamboo on the outside and a wood core in the center, so you're actually getting the stronger fibers on the outside. And to me, that's all just an evolution of what I was talking about there earlier about a fiber optimized design. So I think that's exciting. I've seen a sweet spot for their panels right now. If anytime you're thinking about a 3-ply CLT, they have a kind of a thin bamboo product right now that's great. They also have one coming out that would be, when you think about thicker 5 to 7-ply CLTs, creating one of the layers in bamboo as opposed to pine, and creating some integrated applications between them. I would defer to BAMCOR on the other applications for their panels, but what I love to see is a strategic use of fibers and a mixing of the materials and using the fibers where they're best. And I think they're really spot on target with that idea.
Great, thank you all. We are right at the end of the session, and there's some really great questions still remaining in the Q&A. What we'll do is we'll ask the panelists to answer those questions later on, and then we'll be able to post that to the CarbonPositive website. So with that, thank you all, and we'll look forward to seeing you in the later sessions. Thank you.